Ladies and gentlemen, please welcome Eric Starkloff.
The world connects wirelessly. In fact, mobile broadband connections now outnumber fixed broadband links by nearly 2 to 1. And there's over 5 billion cell phone users in the world. That's 75% of the world's population. Now, it's not just the world of communications that's being revolutionized through technology. You see this increasing pace of innovation in all the new medical devices being designed, in novel ways to produce energy, and in new safety systems for aircraft and automobiles. All of these systems have some common components that are making them more intelligent. Essentially, I/O, processing, and communication. You see, we're digitizing the world around us, and we're using digital technology and software to solve these complex challenges. You know, once we turn something into a digital problem, we can apply Moore's Law, and we get the exponential increase in performance that predicts. And once we apply software to a problem, we can solve it faster and iterate more quickly. And when we connect things, we're able to tie into ecosystems. You know, most of those applications I mentioned on my phone were not built by the vendor of the phone. And in the medical industry, an ecosystem means that a specialist can get access to medical information to do a diagnosis through digitized medical images and sensor data. Now, all of you in this room are designing these type of systems. You're digitizing the world around you. You're connecting things in a variety of applications, from test and measurement to monitoring and control, embedded systems, and robotics. You're doing this with a very diverse set of I/O, and you're doing it with a common platform and a common development tool in LabVIEW. One platform to solve many applications. We call this approach Graphical System Design. And the goal of Graphical System Design is to accelerate the development of any system that needs measurement and control. Now, key to accelerating this productivity is a concept of abstraction. So I want to spend just a moment here talking about abstraction. Now, this has been part of our profession, engineering, since the very beginning. Engineers classically carry around notebooks to document their inventions. One of the most prolific and recognizable of these comes from Leonardo da Vinci. He had over 13,000 pages in his notebooks, all different types of inventions. He's credited with the invention of the helicopter, the parachute, and believe it or not, the first humanoid robot. Now, in his day, inventing these mechanical systems could more or less describe the complete system with a drawing and some notes. But now the systems that we build are way more complex. You know, an Intel 8-core Xeon processor has over 2.3 billion transistors. So clearly, understanding that system down to the lowest level of the transistor is beyond our capacity. And consequently, with all of this complexity, we sometimes get lost in that complexity and may even lose touch with the core of what our engineering profession is all about, which is finding novel solutions to problems. I had a test engineering manager recently tell me that some of his test engineers sort of lose sight of what their job is all about. They think their job, he said, is to build test systems. But he said it's not. Their job is ultimately to ensure the quality of the products we build, and building a test system is really a means to that end. But in order to deal with that complexity and be productive, we need better tools to design and test these systems. Now, most systems still start today with a graphical abstraction. The modern-day example of that notebook is a whiteboard. We start and we diagram up a system and the components and how they're interconnected. And the inspiration of LabVIEW was to create a tool where we could make that abstraction, that innovation, or that invention, also an implementation, where the diagrams can actually run. Now, as engineers, though, sometimes we're skeptical of abstraction, right? We have an expression internally that one man's abstraction is another man's obstruction. You know, we want to be able to have that abstraction, but we also need to be able to drill down to the correct level of detail, all the way to the pin if necessary. If you're designing a new control system, for example, you may need to design the advanced control algorithms down at a very fine level of detail, but you want to abstract the I/O and the user interface so you can quickly iterate on your design. Now, we fundamentally believe at National Instruments that tools should not limit innovation and scientific discovery. The tools need to provide the right level of abstraction, and they need to let you have the flexibility to drill down when necessary.